So what actually happens when your application's data just outgrows its container? If you spend any time at all working with arrays, you know they can sometimes feel like these rigid, unyielding boxes. You declare a size up front, and well, that's kind of what you're stuck with. But in the real world, applications grow, data shifts around, and we desperately need data structures that can dynamically adapt on the fly without breaking a sweat.
Welcome to today's Explainer. We're diving into Chapter 3, Demystifying Linked Lists. This is absolutely one of the most fundamental and honestly most fascinating dynamic data structures in all of computer science. We're going to decode exactly how they free us from the limitations of fixed memory and give our code the flexibility it really needs.
Here's our roadmap for this session. 1. Beyond the fixed array. 2. Anatomy of a linked list. 3. The art of insertion. And 4. Deletion and doubly linked lists. All right, let's jump right into section 1. Beyond the fixed array. Okay, let's dive right into this and look at what's at stake. If you think of an array as a single rigid shipping container where everything is packed tightly together, a linked list is much more like a customizable train. With an array, the size is completely fixed, which can end up wasting a ton of memory. Plus, inserting or deleting an element takes O of n time, because you literally have to shift all the other elements out of the way. But a linked list? It's beautifully dynamic. Insertion and deletion happen in O of 1 constant time because there's absolutely no shifting required.
And you can really see the difference when you look at how they live down in memory. Arrays demand contiguous memory locations, blocks 100, 101, 102, all perfectly lined up in a row. But the linked list just dynamically scatters its memory. The first item might be at block 490, the next way over at 500, then 510. They don't need to be neighbors at all because they just find each other using explicit memory addresses.
Which brings us to section 2, anatomy of a linked list.
So everything in this structure revolves around something called a node. You can think of a node as our individual train car, and it has two very specific jobs. First, it holds the cargo. That's the actual data you want to store. Second, it holds the hitch. That's a reference or a link to the very next node in the sequence. Oh, and the very first node in our entire train, we just call that the head. Now, what's really interesting here is the visual split right down the middle of the node. On the left side, you have the value. That's storing your actual data. But on the right side, you've got the next pointer. It literally just stores the memory address of where the next node lives. And if there is no next node, it just points to null, signaling the absolute end of the line.
Moving on to section 3, the art of insertion.
Let's say we want to pop a brand new node right at the very beginning of our list. In C++, this breaks down into 3 pretty simple mechanical steps. Step 1. Create the new node in memory. Step 2. Take this new node's next pointer and point it directly at whatever the current head of the list happens to be. And Step 3. Update the official head pointer so it recognizes your newly inserted node as the true start of the list.
Let's actually visualize that first step. Here is our very first train car, created fresh in memory. It's node 1 holding a value of 5. Now, because it's the only node that exists right now, its next pointer points to absolutely nothing, null, and our head variable is pointing directly to it.
And this brilliantly illustrates the magic of inserting at the beginning. We create a new node, node 2, holding the value 3. We can easily couple this new car to the front just by taking its next pointer and redirecting it to node 1. Then we simply update our main head pointer to point to node 2. And just like that, boom, we've dynamically grown our list in O of 1 constant time. No shifting required at all.
But wait, what if we want to insert at the very end of the list? Well, we create node 3, giving it a value of 7. But to actually connect it, we can't just teleport there instantly. We have to start at the head and traverse through the entire list, node by node, until we hit a node whose next pointer is null. That traversal means inserting at the end takes O of n time. Once we finally find that last node, we simply change its next pointer from null to our new node 3.
Inserting right into the middle is honestly just as elegant. Say we want to wedge node 4, holding the value 4, right into the second position. We traverse to the node just before our target spot. We make our new node 4 point to the node currently occupying that spot, and then we just update the previous node to point to node 4 instead. We've seamlessly wedged a new node right into the middle of the chain, just by updating 2 pointers.
All right, on to our final section, part 4, deletion and doubly linked lists. So, deleting a node, let's say the head node, is kind of funny. We don't actually erase the data right away.
We simply tell the head pointer to completely bypass the first node and point directly to the second node in the chain. The old head node is unceremoniously cut off, left floating in the void until we use the delete command in C++ to permanently banish it from memory. So far, we've built an incredibly flexible structure, for sure. But there is a catch. A singly linked list is a one-way street. Every node only knows about the node in front of it. It has zero awareness of the node behind it. But what if we need to traverse backward through our data?
This is exactly where we upgrade to a doubly linked list. While a singly linked list only lets you travel in one direction, a doubly linked list lets you traverse both backward and forward. Think about real-world applications here, like the back and forth buttons on your web browser's history. To make that work efficiently, the underlying data structure absolutely needs to flow in both directions.
To make this happen, we need to upgrade our node's anatomy. Our new doubly linked node struct still has the data value and the next pointer, but we've added a crucial third element, the prev pointer. This explicitly stores the memory address of the previous node in the list.
Let's see how this builds out practically. We've got dual pointers connecting our nodes now. Node 2's next pointer aims at node 1, and node 1's prev pointer aims right back at node 2. We also introduce a tail address to keep track of the very end of the list. That makes it incredibly fast to jump straight to the end and start traversing backward. So the crucial point here is that with this extra power comes, well, extra responsibility. When you delete a node from a doubly linked list, like removing node 2 from the beginning here, you can't just update the head pointer. You also have to grab the new head node, node 1, and carefully update its prev pointer to null. You really have to manage both the next and prev pointers simultaneously to keep the whole chain intact. Which leaves us with a pretty fun puzzle to wrap up on. Based on everything we've explored today about O of 1 constant time insertion versus O of n traversal time, which underlying data structure, an array, a singly linked list, or a doubly linked list, would be the absolute best choice for implementing a stacks push operation or a queues NQ operation? Think about where you add data and exactly where you remove it. I'll leave you to ponder that one. Keep coding and keep optimizing.